Large hail signatures are much less complex than tornado vortex signatures, but they can be equally important to look for when storm chasing. One of the most basic signs that hail may be occurring within a storm is an increase in reflectivity. This can happen both at the lowest elevation angle and aloft. In fact, increasing reflectivities above about 10 to 20,000 feet off the ground is a reliable signal of large hail production. Typically, large hail is associated with reflectivity values in excess of about 55 dBz. However, just because reflectivity exceeds this threshold within an area of precipitation does not mean that hail is actually falling, as heavy rain can yield similarly enhanced reflectivities. This is where dual polarization products come in. Because radars with dual polarization capabilities can decipher the horizontal and vertical characteristics of targets, they can often differentiate between rain and hail. Differential reflectivity is quite effective in analyzing storms for large hail. Because large hailstones tend to be somewhat spherical and tumble as they fall, ZDR often decreases to near zero in areas where large hail is present.
Don't learn storm chasing alone. Go where chasers are already talking. Discord community link in description.
Although not as reliable as ZDR, correlation coefficient can also be used to identify areas of large hail. In a volume that contains a mix of rain and hail, or one that consists of giant hailstones with irregular shapes and sizes, the similarity in the characteristics of targets decreases relative to that of a volume of all rain, which yields decreased correlation coefficient values generally below 0.95. These products should be used in tandem with base reflectivity. Areas of depressed differential reflectivity and correlation coefficient associated with hail will always be coincident with intense reflectivities. In supercells, large hail is most often found just downstream of the mesocyclone and hook echo if one is present. Small hailstones, generally less than 1.5 to 2 centimeters in diameter, are often coated in lots of water and therefore return increased power back to the radar. Thus, they often appear similar to giant raindrops on radar with high reflectivity and ZDR, so if you see significantly enhanced reflectivities within a storm, say above 70 dBz, it often represents large amounts of small hail rather than large to giant hail. However, large to giant hail can sometimes be associated with these significantly enhanced reflectivities, and dual polarization products can help us determine whether or not this is the case, as discussed earlier. One signature in particular that's an extremely reliable indicator of large hail is a three-body scatter spike, or TBSS. A three-body scatter spike, also called a hail spike, appears as a spike of slightly enhanced reflectivity that protrudes out the side of the storm opposite the radar. A TBSS is not comprised of precipitation or actual meteorological targets. Instead, it's an artifact that sometimes occurs as the radar beam interacts with large wet hail. As energy within the radar beam hits large wet hail within a storm, some of it gets reflected toward the ground, then back to the storm, then back toward the radar. It's scattered 3 times, hence the name three-body scatter spike. This portion of the energy returns to the radar slightly after the remainder of the energy returns, so the radar thinks that these echoes are slightly farther along the radial than they actually are, creating the spike on the side of the storm opposite the radar. A TBSS will also show up in other radar products, including velocity and the suite of dual polarization products. Notice the significantly decreased correlation coefficient within the TBSS, indicative of non-meteorological returns. We're going to move on to damaging straight-line winds. They may not get as much notoriety as tornadoes, but they can be equally as impactful, so it's important to know how to analyze radar data for strong straight-line winds. The velocity of a target that's displayed on a radar program will almost always be slightly less than the actual velocity of the target. This is because radars are at fixed locations, meaning that they can only measure how fast a target is moving toward or away from the radar itself, i.e. along a radial, hence why it's called radial velocity. Therefore, when you're analyzing velocity data for potentially damaging winds, the radar may slightly underestimate the actual winds within a storm or storm complex. On the flip side, the velocities that you see at the lowest elevation angle are almost always stronger than what actually reaches and spreads out along the surface. Remember that the radar beam gets farther and farther from the surface the more it extends outward from the radar site, so even if you're analyzing data at the lowest elevation angle, you're still getting a look at the storm that's quite a ways from the surface, especially if the storm is somewhat distant to the radar site. Also, friction from topography and land cover that occurs at and near the surface can cause winds to decelerate. Finally, remember that the greater the angle between the radar beam and the target's motion, the less the portion of the target's actual velocity that will be sampled, and the less the radial velocity will be. If a target is moving perfectly perpendicular to the radar beam, its radial velocity will be 0. So, if you're analyzing an intense storm complex that you think might be producing damaging straight-line winds, but don't see any evidence of damaging straight-line winds on radar, check to see if the winds are blowing more perpendicular to the radar beam. With these notes in mind, let's get into some signatures that can accompany damaging winds on radar. The first of these is a downburst signature. As the strong winds within a downburst reach the surface, they spread out both toward and away from the radar. Therefore, downbursts are accompanied by localized divergence signatures in velocity data, within which an area of enhanced outbound velocities lies adjacent to and on the far side relative to the radar of an area of enhanced inbound velocities. The areas of enhanced inbounds and outbounds tend to spread apart from one another and weaken with time. Base velocity should be used to interpret downburst signatures, unlike rotational signatures, which are best analyzed via storm relative velocity. At the center of the downburst, enhanced reflectivity values and an increase in KDP may appear as well. These are associated with the cascade of heavy precipitation that often accompanies a downburst. Downburst production within a storm is a sign that that storm may be outflow dominant, which is unfavorable for tornadoes. Damaging winds are often the main hazard in linear convective systems, and there are a number of signatures that can help indicate whether or not a QLCS is producing them. Strong downdraft winds can force part of or even the entirety of a squall line to bow outward, which is called a bow echo. Portions of QLCSs that bow outward are often associated with more intense surface winds than other areas of the line. Bow echoes tend to feature a very strong, tight reflectivity gradient on their leading edge. In addition, significant damaging winds are more likely if the gust front or outflow boundary associated with a QLCS or specific bow echo remains close to the leading edge of the complex. An outflow boundary that surges well ahead of a QLCS or bow echo, as in the southern portion of this QLCS here, is not as favorable for significant damaging winds, as it tends to diminish updrafts within the line and decrease the overall intensity of the complex. A common feature of bow echoes is a rear inflow jet, which is a current of fast-moving air that feeds into the backside of a QLCS, originating aloft and often descending down to the surface, causing the complex to bow outward. The most intense surface winds often occur along the rear inflow jet at the apex of the bow. Because the rear inflow jet is often cooler and drier than the surrounding air, it can enhance downdraft strength within the QLCS via evaporative cooling, leading to more intense surface winds, and it can also allow the QLCS to accelerate and persist for a longer duration. On radar, the rear inflow jet is manifested as an area of enhanced velocities on the backside of an ongoing bow echo, both at the lowest elevation angle and aloft. Sometimes rear inflow notches develop, which are small channels of weak reflectivity in the lowest 1 to 2 kilometers above radar level that signal the arrival of the rear inflow jet at the surface and represent localized enhancements of the winds within the rear inflow jet. Tornadic circulations often occur just north of the apex of the bow.
Remember to check out those links in the description below, and then watch another video.